Now, if we want to construct lists, we've already seen one way, and that's what we're doing over here with list A, B, C. Gives me the list A, B, C. There are other ways. Cons will return a cons cell. If I say cons nil, it will give me an error. Okay, we won't worry about that. Oh, because I didn't give it two things. If I say cons nil to nil, it will give me the list whose first element is nil, which is weird. Probably should tell you what it does first. What it does is it creates a new cons cell and makes the first element, first pointer, point to the first argument, and makes the second pointer point to the second argument. Now, that second pointer, remember, points to the cdr of the list. So it's going to make the list BC, in this case, the cdr of the list, whose first element is A. What is that going to look like? Well, it's going to look like that. So it essentially doesn't push, I'm sorry, there's another function that does that. It essentially takes this and creates a new list with that element stuck on the front of it. Okay? Push, by the way, is a destructive function. If I say seq A 1, 2, and I say push 3A, then it pushes it on there, but now A's changed. Cons is not destructive. Okay? Alrighty-dighty. So what we're doing here then, and pretend I didn't just say that, what we're doing here then is just consing things together. We call it consing, for example. Here I'm putting the first pointer of this cons cell I'm creating points to A, the second points to nil, which means that's the list with no cdr. Okay? Consing nil onto something will indeed cons nil onto it. We can cons list onto it. We can also do this, cons A, B. What do you think that's going to give us? If you said dotted pair, you're right, because the first thing in the cons will point, in the cons cell will point to the atom A. The second thing will point to the atom B, and so we have the dotted pair. Okay? Another way of creating lists is to use append. All right, so we can append two things together. In this case, it's as if we just joined these things together, which we do. And so here we have that, the list there. And take as many lists as you want and append them together. If you append nil to something, that's an empty list. Appended onto the front of that's just the list itself. If I append that to that, I get an error. Can't append two things that one of them is not a list, etc. Okay? And then we've seen lists before, how you can do that with. We just did that. All right? Now, with variables in languages, we have the ability to store temporary or permanent things. Lisp technically doesn't have variables, although we call it that. It has symbols that you can bind to a value. Essentially the same thing for our purposes. Okay? So symbols are what hold contents of variables. Symbols have several different cells associated with them. One of those cells is the value cell. Another one can be a function cell. And so we can just as easy have, say, we set Q A to 1, and we can also define A to be this list, and it doesn't care. It knows what context we're in. Okay? So there's different cells. We will see one other later. We've already seen what happens if we have a symbol that has no value and ask it for the value. We get this wonderful error that we have, the unbound variable error. So a symbol that has no value is called an unbound variable or an unbound symbol. Okay? If we want to see if something's bound or not, we use bound P. And that P at the end there usually means a predicate of some sort, something that returns true or false. So if I say bound P A, it says yes, A is bound. It has a value. If I say bound P this thing, it will tell me nil, is not bound. So you need to use this sometime if you're about to evaluate something and you want to find out if it has a value before you do it. Okay? To set a variable, there's a couple different ways. The first way is set. What that does is set the contents, the value cell of this symbol, whatever that happens to be, evaluate to be the value that this evaluates to. So if I set A to B, it returns the value B. That's just telling me everything returns a value in the list, so it's telling me I'm returning that value from set. Then if I type A, as you expect, it says your value is B. Okay. Now let's see if I do something else. If I say set A to 1, and I type 1, I mean, it gives me back 1. If I type A, now you would expect it to return B, right? Why? Well, because, remember I said this sets whatever this evaluates to whatever that evaluates to. A was set to B. I didn't put a quote there, so this evaluates to B. And then it sets B to be equal to 1. So if I go down here now and type B, I get 1. Well, this can give you some nightmares when you forget a quote somewhere. So it didn't take people very long to say, plus it's ugly. It didn't take people very long to say, well, we're going to use a new function called setQ, set quoted. And there I don't have to put a quote there. Okay, so it does the thing you'd expect it to. There's a different setting function that's somewhat more general, setF. This will set, if it's given an atom here, a symbol, I mean, it functions exactly as setQ. Okay. However, if I give it something else that results in a pointer, or that it can actually find, it will set whatever that evaluates to, not just a symbol, but it'll set whatever pointer that is, whatever reference that is, to be technical, to this. So in this case, it's set the car of A, I've made A1, 2 up here, it sets the car of A to be 3, and if I type A here, it will tell me that it's actually set it. We saw that over there when I did something else too. Okay, that's pretty useful. Predicates, we talked about some examples. You can check to see if something's an atom. So for example, atom A, yes, as you expect. Atom A, what is A? So it is. Foo, still got that? So let's see, atom foo is not because it's a list, okay? Symbol, P. Yes, that's a symbol. Symbol P evaluated A isn't because A is 1, for example. List checks to see if something's a list. Cons checks to see if something's a cons. And so if you want to see if something is a value is a dotted pair, you would check to see if it's a cons, but not a list, okay? String checks for string. Null sees if something is nil. So for example, null, nil is true. That's the same as this, actually. Null and nil, or not and null are the same one, but they're sometimes useful to call it null in some contexts if you mean nothing's in there, and other times if you mean it's false, okay? And has the typical relational operators that you find in any language, so prefix may screw you up a little bit, but that's asking if 3 is less than 4, okay? All right, equality, we mentioned that the kind of equality that member uses by default is EQ, or is identity. EQ is identity. So it does this, it does nil, because we're creating those two cons, we're creating those two lists, really, and they're two different places in memory, so it returns nil. We can do this, we can set A to be this, we set B to A, and now these two things are actually the same memory, so that's true. Fixed nums, which is Lisp word for integers, can be equated via EQ, but not floats. Floats are a little problematic anyways. They may not be quite the same representation inside or something like that. They're certainly in different places everywhere, whereas some of these may not be in different places. Some of the low integers may be stored in the same place. And so there we have an example of where EQ doesn't, even though it looks like it's equal, is not EQ equal. We can also use EQL, and what this does is extend EQ a little bit, and it says if the two things I'm equating are EQ equal, or identity, then yes, that's true, or if they're the same type and the same value, okay? So character objects or something like that. This is true in either of them. This happens to be true in EQL, okay? And the truly general form of equal is equal, EQUAL, and it says if the two things are EQL, then yes. Otherwise, if they are the same structure and have the same and all their pieces are EQUAL. So it works just like this for any of these, but now notice these two things are now equal because they're the same structure and they have the same contents, essentially, same contents. These two things also are equal because it goes down through here and checks. Why wouldn't you always use this? Well, it's slower, because you might figure out it's trying to do a bunch of stuff in here, and if it checks something like this, then it may take longer than EQ, will take longer than EQ or EQL. And there are some times, of course, when you want to just see if something is the same thing, and the only way you can do that is with EQL or EQ. Okay, that's just more stuff. All right, we have our share of Boolean operators, so not, or, and are the primary ones. And so just as you'd expect, these are short-circuiting operators. And so if I say or, nil, nil, t, a, b, c, where those aren't even defined down here, then it will complain bitterly. This is the compiler complaining, but it will actually do it. And it'll complain again just the same way. But if you notice, if you ignore all this crap here, which we'll just ignore like this, yep, you won't. We'll ignore like that. If I didn't have the compiler errors, this is what I would have seen, and not errors, warnings. What it did was, well, this isn't true, so it keeps going. This isn't true, it keeps going. This is true, so it stops. And even though some of these aren't bound, it doesn't evaluate them. Okay, so you're familiar with this from Python, probably. And is also short-circuiting. And t, nil, and then some crap out here. And that also, if you, didn't give me grief that time. This also then returns nil, or returns nil rather, because this is true, so it keeps going true. Nil, it stops right there. Okay. All right. The primary way of checking, of conditionally executing things, of a conditional statement in Lisp is cond. It is this form, cond, and then a set of test action clauses. It will be 0 or more of these. The first one of these whose test evaluates to true, it will do the action part if there is an action. If there's not an action, it just returns whatever the test evaluated to. If there is an action, this can be as many Lisp forms, that is, statements. We don't really talk about statements in Lisp, but Lisp forms, things that evaluate to a valid Lisp expression. It can be as many of those as you want. It will return the value of the last one. So down here, here's a cond statement that says if or this is true or that is true, it's going to print clause 1. Okay, so if a is equal to 1, 1, 3, and the length of a is less than, or the length of a is less than 4, it will return, it'll do this part of the clause, the action part, and print clause 1. Otherwise, it'll skip down to this. Now, if that is true, it skips, when it's done with the clause, it skips out of the cond statement. Here, if it's not true, it jumps down here, checks that one. If that's not true, it jumps down here. But this t here is going to always be true. It evaluates to true. And so this is like an otherwise or an else, and it prints the clause 3. Okay. Now this is, in modern languages, this would be represented by if all of this, else if this thing, else this thing. Okay, but Lisp does it slightly different. There are if statements in Lisp. They are somewhat weird. Oops. If t, then else. They're like this. Okay, and you can only have one thing in each of these places. Okay. Now, as you know from other languages, there are grouping constructs in languages that allow us to take multiple statements and make them one statement. Well, there's the same thing in Lisp. They can take multiple forms and make one form out of them. We'll talk about that in a minute. We also have when, which is just syntactic sugaring, really. So when equals a3, do this, print high. A is not 3, so don't do that. But if I say 3, 3, it'll print it. And then we have unless, which is the opposite. And we can also use or and, of course, for conditionals because they're short-circuiting. All right, now, if you go back to Lambda a minute, remember we had those Lambdas, and I said we don't want to use those. We end up using defuns. It turns out they're actually quite useful. We can call Lambdas this way. First of all, we can build these things and then execute them. And so if we build something and execute it in the language, we've just wrote a program that writes a program. Okay, so we can do that. Lisp is used for that sort of thing. Here, this is applying this function to 4, so just a square function for that. Here is applying that function to this. If I use the function apply, it takes this first argument, which happens to be this lambda form, as a function, and it applies it to this list. This thing should be a list. It's as if I had called this inside of that first parenthesis. Okay? And so there can be as many arguments as you want inside this parenthesis in this list. Funcall is another one that does essentially the same thing, but instead applies this lambda to, and this could be a function name as well, applies this lambda to as many arguments out here as I have. So for example, I could say apply, I'm using this hashtag there. That's just a compiler directive telling Lisp, hey, this is a function coming up, so optimize yourself for it. So I can apply that to the list 3, 4, for example, and that should give me 7. Or I can do funcall, and now just leave that off, 3, 4, 5, 6, whatever I want, and I get that, okay? So you can do it with lambdas. Now, why would I ever want a lambda? Well, let's take a look at this. Suppose we wanted to see if there's a list, if A is anywhere in here, or if A is in, if this thing is, if an element is a list, and its first element is A, that's what I'm looking for. Well, you can't do that with member unless you specify your own equality function. So here, or your own test function. Here, I'm specifying, look at each element of this list, but instead of applying EQ to it, apply this thing to it. So this lambda form, again, this is a compiler directive just saying, Hey, this is a function. So what I'm taking there is I'm taking this lambda and applying to each one of those with the first thing, the first argument will be this thing, and the second argument will be the element of the list. So if the thing is a cons, then I'm going to check to see if the element is a cons, rather, I'm going to check to see if thing is equal to the car of it. So that would match this. If the thing is not a cons, since this is short-circuiting, it's just going to return nil, and it'll move on to the next one. And so this will find that A in that list, okay? That will return that. Now defun has a general form. Looks like this. We've seen simple defun so far. You can also have more complicated things. So for example, I can say defun foo, A, and optional B. So something like that. And if I say foo 1, 2, then as you'd expect. And if I say foo 1, it's optional and has nil. You can specify values for this by giving a list like this. And that now says if I have a default, I'll make it 14 if I don't specify something else. Okay? You can specify rest arguments. And what that means is every other argument now gets crammed into a list that's put into this variable b. Okay? So if I do foo1, nothing. If I do foo, let's see if I can do foo with something else in there, 1, 2, then b contains the list 2. And if I did this, you get the idea, right? Okay. And then keyword arguments is how we do, well, keyword arguments. It's not as forgiving. Lisp is not as forgiving as Python in this. Remember, anything can be a keyword argument or a positional argument. In Lisp, you pick your battles. So here, let's go back up here to redefine foo again, if I can find it. I'm using meta p to go backwards. Oh, it didn't like me. Okay, that's cool. There we go. So, oops, I'm now making b a keyword argument. And if I call this like this, nil has no value. It has no value. If I call it this way, it's going to give me an error. So I have to say the name of the thing, and now it does that. Okay, and you can mix and match these, but if you're going to take a look at a good Lisp reference, it's not as easy as it's not as simple as it might seem.